is equal to work done divided by the charges moved, because we want the work done to move a unit what? A unit charge. Now, having said the meaning of these two quantities, current and voltage, we now want to perform an experiment to determine whether these two quantities have any relationship. And this experiment that we want to perform is called Ohm's law. Ohm's law. So we are going to use a number of devices, and those devices are right in the groups. They have been shared. I want us to confirm that we have each of these devices. We have just mentioned that we measure in current, we shall require an ammeter. Do we have an ammeter in our tables?
Yes.
Yes, we have our ammeter. Now, I didn't ask which device do we use in measuring voltage. Which device do we use to measure voltage? Voltage. Yes. We use a voltmeter. Do you have one in your setup? Yes, we have one. You can check the ranges of the voltmeter and the ammeter. The ammeter has a range from 0 to 1, but we also have another scale giving us a range of 0 to 3. So in our experiment, we are going to use the range from 0 to 1. For the voltmeter, since we are using 2 cells, and the cells are new, giving us a total voltage of 3, we are going to use the range from 0 to 5. Okay? In our relation. But just before we go through the worksheet that I have given you, I want us to remind ourselves how to measure current and how to measure voltage. So I want you in your groups to do a simple circuit just to measure current. Without including the other components in the device. I just want you to use a switch, the cells which are already mounted in your cell orders, and then the ammeter. Just those three. Just connect those three and see whether you can be able to determine the current flowing in the circuit. I hope you remember how to do the connection. A switch, an ammeter, and the cells. I've drawn a circuit diagram on the board. You can follow it. Do that simple connection. From the positive terminal of the cell, you connect to the ammeter, from the ammeter to the switch, and then back to the negative terminal of the cell. Check whether that ammeter is okay, it's working, and be able to give you current flowing in the circuit. Any group that has succeeded in doing this? Is it measuring when you close the circuit? Are we okay? What is the current in your connection? Yes. Remember how to interpret the scale? Just to assist us in interpreting the scale, we have from 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is where we have 0.2. So that means 5 divisions, we are at 0.1. And therefore, per division, we have 0.02. So this one will be 0.02, 0.04, 0.06, 0.08. Then we go to 0.1. Okay? So for example, if your pointer is there, what will be the reading? If your pointer is at that mark, what will be the reading? 0.02. No, is that 0.02? No, it's 0.04. Because 0.02 is this one. 0.04, 0.06, 0.08, then we go to 0.1. So yours is working, it is okay. Very well. How about you? Bukasawa. What about you? What is the current in your ammeter? 0.02 or 0.02? 0.2 from that team. How about you? What is the current?
Tumetumia 3. So you use this scale. Inatoka 0 mpaka 3. Juu tumetumia 3. So tumetumia 1. Tumetumia 1. So juu. Kwa sana. Soma scale ya chini. Haifiki 1, sindio? So you can use this one. Sasa nasoma scale ya juu.
So those who have finished checking the current, you can do the same and try to check the workability of your voltmeters. Check the voltmeter. Check the voltmeter. And remember, as you check the voltmeter, that whereas we connect an ammeter in series in a circuit, a voltmeter is supposed to be connected in parallel. Don't forget that. Don't forget that. So we shall, because we are checking the EMF across the cells, we shall connect the voltmeter across the cells and see what reading it will give us. In that case, you don't need the switch. You don't need the switch. That's just a direct connection from the positive terminal of the cell straight to the cell. That's a very simple circuit. From the cell to the voltmeter, from the voltmeter to the cell. Try and do that. See how much voltage our cells have. That is now what we call in Form 1 an electromotive force, US. 2.1 for this group, 2.1 volts for this group, 1.9 volts. Let's hear from the other group. Yes. What do you have?
1.3.
1.3. 1.3 from that group. How about the last group? What voltage is your ammeter giving us? You said this is just a direct connection. You don't need this, you don't need the switch. That connect directly to the cell and check what. Yeah, there you go. So get that reading. You have connected to which terminal? You have used 3, eh? So which scale? The upper scale, eh? So for the upper scale, what is the reading?
2.5.
Yes, what is the reading?
2.5. 2.5.
2.5. So I think with that now we are okay. We can measure current, we can measure voltage, and those are the key quantities that we need in verifying Ohm's law. So without now wasting much time, I want us to follow the circuit diagram in the worksheets, and we do that connection. There is a circuit diagram in the worksheets. I want us to follow it. We come up with the circuit that we are going to use in investigating the law that we want to investigate. Now, in the worksheet, there is a conductor that has been named T. That conductor is now going to be our resistance wire, and we are using nickel. We are going to use that. It is denoted by letter T in our circuit diagram. And then I have chosen in the place of a rheostat, because that is what we have in our worksheets. We use a potentiometer. It's also a variable resistor. Okay? It has 3 terminals. When you look at it from the side, we have this terminal at the end, we have this terminal at the end, and we have a terminal at the center. Okay? Now, when we use these 2 terminals, it becomes a fixed resistor. But in our case, we want to use it as a variable resistor. So we are going to use one of these at the ends and the middle one. One of these terminals at the end and the middle one, so that we have 2 terminals. Are we okay? Let's go ahead and do the connection. I will assist you in case there is a problem. You can raise any concern that you are going to have. Follow the circuit diagram the way it is in your worksheets. Remember not to interchange the terminals. Just connect the way they appear in the worksheet. If you see a deflection in the anti-clockwise direction, remember a deflection in that direction is an indication of wrong connection. So basically that is what you are supposed to have. I want you to follow the circuit from some point. For example, if you move from the positive terminal of the cell, bring your wire to this is a variable resistor, now the potentiometer. From the potentiometer, let it move to the resistance wire. You have already coiled your wire. Yes. Then from there, let it move to the switch, to the ammeter, and then back to the cell. Then the voltmeter is going to be connected across the resistance wire. This is the resistance wire, which we have said we use nickel. This one is our switch. This is the ammeter. This is the battery. We say when we have several cells connected together, we form a battery. And then this one here is our variable resistor. Those are the devices. In case you have any challenges, you can let me know. Are you okay? Your circuit is good. coming up with the circuit. Confirm whether your voltmeter and ammeter are measuring the respective quantities. Are you okay? To the resistance wire, which is this one. Then from the resistance wire, we move to the switch. So can I have this one move to the switch? This one. Okay, move to the switch. And from the switch, you are moving to the which is yes. Are we okay? Any team with a problem? Yes, just a minute.
Hii ni positive. So hii ina face kanisa kwa ndio ya kutoka this should come directly here. Then from here, come to the switch. What is this?
Yes.
Anafungua hii. Start.
Then you can now from here to circuit using the switch and see whether it's ammeter and voltmeter are working. Very good. Let's see what is happening here. Two groups are already okay now. And your machine's working. Well, just hold it at that point. Are you okay? Let's give them a minute. They complete their connection so that we can move together. Once you have connected your circuit, what is the worksheet saying? Somebody to read for us. from the worksheet. Number one was to set up the apparatus as it appears in the diagram, circuit diagram. What should be the next step?
Close the switch and adjust the current flow to the connect circuit using the rear start to the least possible value.
We set up the current to the least possible value. So that is what we are going to do next. As soon as they are okay, we shall move to that stage. Is it working now? The ammeter, the voltmeter. Check the connection in the potentiometer. We said we use the middle terminal and any of the other two. Are they now working? Good enough? Very well. So we are now going to progress with the activity. We said the first step is to set up the current to the least possible value. Now that is being done using the variable resistor. So we are going to use this part. You try to rotate it, see what is happening to the deflection, both on the ammeter and the voltmeter. When you try to rotate it, that is now varying the resistance. What is happening? Is there a variation of the current? And can you see the current vary? How about the voltage? Very well. So I want us now to set it to the least possible value. Rotate it until you get the least current. The least. Okay? Then now, you have a table in that worksheet. A table giving us current and voltage. We have the current I in amperes. We have the voltage V in volts. So I want you to record that first current. That least one that you have set up. Record it. And you also record the corresponding voltage. So in this first space here, you record, for example, unit is 0.02, and then the corresponding voltage, if for example it is 1.5. Those are the values I want you to record in the table. Any group having a challenge in doing that? We are going to record the current and the voltage for that least possible current. Have you recorded the current, the voltage? Here you have it. Are we okay? Have we done the first record? Very well.
Hey, why is this positive to positive?
Now, I want you to adjust slightly to the next current. Just a slight adjustment so that you have a different current. Jaribu kuongeza current kidogo.
This is the positive.
Just a slight adjustment so that there is a change.
Which is the positive?
Current. When you are trying to adjust, are you seeing any variation in the current? Are you seeing any variation?
So we connect to
Now record the next current
iko opposite.
against the corresponding voltage. Let's say, for example, this one has moved to 0.03. You record 0.03. Record also the corresponding voltage. For example, if it has moved to 1.6, are we okay? Now, can we move on with that procedure and fill the table? How many more values do we have? How many more values? 3 more values. So now, move on in that manner and fill the remaining 3 values. Vary the current, and the corresponding
What is
voltage.
missing?
Are we okay? Any problem? As you vary the current, I hope you are able to notice a change in the voltage.
Look at
From left, vary it again, for the current voltage. Like it has now moved to what?
try here. What is the problem? Yeah, the positive.
Continue with the process until you fill all the values in the table.
Variable resistor to wire.
Are we okay in our case?
Here to switch.
The code fits the table.
Working.
You are done? You're almost there.
Now connect the other way sasa. Badilisha terminals.
So this group has already finished filling the table. We are waiting for the others to finish so that we can have a
Badilisha
presentation
terminals.
of the results. So you can agree on one member from the group to do the presentation of the results that you have in the table.
Still nothing. Naona inaenda opposite.
You are
Kumaanisha
group also.
hapana.
So what?
Hii hapa. Hii hapa.
Are you done with the recording the values? You are on the last one. How about this group? Are you okay? Try to vary the current, see what is happening. So check the connection here. And change it. Yeah, it's supposed to work like that. So you set the current to the least possible. Okay, I think we are progressing well, with the exception of one group. The others have filled the tables. Have you agreed on who will do the presentation for the group? Well, have you agreed who will give us the results from this group? Have you agreed? Yes. And have you agreed? The person to give us the results? Yes. Let's give this ones 1 or 2 seconds to finish. We're almost there. Maybe one value to go. Yes, one value to go. Doing well, doing well. Signal us when you are done. So that we can move to the next stage. Group 4. So let us know when you are done. So that you can have the presentations.
0.8. Hivyo ndo mmepata. Kama hiyo ndo mmepata sawa.
That is what I expect. So, are you done now? Now let's have the presentations. We start with the group. Let's start with the group 1. You can stand and read for us the results from your group.
When the current was on 0.04, the voltage was at 0.5. When the current was at 0.05, the voltage was at 0.8. When the current was at 0.06, the voltage was at 1.2. When the current was at 0.07, the voltage was at 1.3. When the current was at 0.08, the voltage was at 1.4.
That is very good. Let us appreciate him. Let's hear from group 2. Let's hear from group 2.
When current was 0.01, voltage was 0.6. When current was 0.02, voltage was 0.9. When current was 0.03, voltage was 1.5. When current was 0.04, voltage was 1.7. And when current was 0.05, voltage was 1.9.
Let us appreciate them for the good work. Good, we go to group 3. Let's get the results for group 3. Zero point 0.5. 0.04.
Voltage was 1.
1.0.
When current was 0.05,
0.05.
voltage was 1.1.
1.1.
When current was 0.06,
0.06.
voltage was 1.4.
1.4.
When current was 0.07,
0.07.
voltage was 1.7.
1.7. Let us appreciate them. Good work. Good work. The last group now. Group 4.
When
Get the results.
current was 0.0,
0. 0.0. 0.0.
Voltage was 0.0.
0.0.
When current was 0.02,
0.02.
voltage was 0.6.
0.6.
When current was 0.04,
0.04.
voltage was 2.0.
2.0.
Current was 0.06,
0.06,
Voltage was
2.0.
2.0. Current was 0.08.
0.08,
2.0.
2.0. Now, that is good. Let us appreciate them. Let us now observe these results. Let us observe the results from all the groups and observe one thing, or not one thing, about the results. The relationship between current and voltage. What is happening? What is happening to the two? And that cuts across all the groups. There is something that we can see from the results of all the groups. What is that one thing that we can see? Yes, Carol?
The two quantities are increasing and relative proportion increasing.
It says the two quantities are increasing proportionately. What that means is when the current increases, the voltage is also increasing. And that one is true for all the groups. Alright? So we can make a conclusion based on what Rudy has told us that when current increases, the voltage also increases. Now, in mathematics, of course, physics borrows from mathematics heavily. This is now what we call direct proportion. Direct proportion. And mathematically, we write it as voltage is directly proportional to current. Voltage is directly proportional to current. And when we want to change now this expression into an equal sign, we now include a proportionality constant. And the proportionality constant that we include here is called R. And R is what we call resistance. So we say voltage is equal to resistance times current. Voltage is equal to resistance times current. So we shall say here where R is the proportionality constant or resistance. Now from this relationship, we now state what we call Ohm's law. We now state what we call Ohm's law. What does Ohm's law therefore state? We now get the statement of Ohm's law from that relationship. We say Ohm's law states that the current flowing across a conductor is directly proportional to the voltage drop across it. Now, when we get to that point, we provide a condition. And the condition is provided temperature and other physical conditions are kept constant. That is now what we call Ohm's law in form of a statement. Ohm's law in form of an equation is V, voltage, is equal to R, resistance, times current, I. That is now in the form of a simple equation which we can use when we are doing numerical questions. This is now the statement that Holmes came up with, explaining the law. Now, our interest is drawn on this condition because we are saying provided. Does it mean that when the temperature changes, the law does not remain true? What do you think? Somebody? If the temperature is not kept constant, like now we have done the experiment within kind of a constant temperature, we are operating within room temperature. Now supposing the temperature changes, either it is increased or reduced, what do you think is likely to happen? Somebody, you can just make a guess. Will the results still remain the way they are? Yes? What do you think? Share with us. Somebody? Yes?
When the temperature increases or decreases, the readings will change.
The readings will change. He says, when the temperature is not kept constant, those readings will not remain the way they are. So this is one of the laws which goes with our condition. And the condition is that the temperature must be kept constant. And not only temperature, but also other what? Physical conditions. Now, we categorize devices into two based on that particular condition. And we say some devices or some conductors are ohmic and others are non-ohmic. Now, the ones which we call ohmic are these ones which would obey the law. The ones which don't obey the law, we call them non-ohmic conductors. Now, to our next step of our activity. What is our next step of our activity? We have performed the experiment, we have recorded our values in the table. What now comes next? We are now supposed to do a graph. We are supposed to draw a graph of voltage against what? Against current. We draw a graph of voltage against current. But just before we do that, can somebody predict the kind of a graph that we expect? What kind of a graph do we expect? When we plot our graph, the graph of voltage against current, voltage in volts against the current in amperes, what kind of a graph do you think this one is going to be from the relationship that we have just talked about? We have just talked about the relationship here, direct proportion from our knowledge in mathematics. When two quantities are directly proportional, a graph of such quantities will be of what nature? Somebody from any group, and especially the ones that have not responded. Catherine says it is going to be a straight line graph. A straight line graph. So we expect a graph which is a straight line. We expect a graph which is a straight line. And being a straight line means it has a constant what? A constant gradient. Now the gradient here, and we know how to get gradient. How do we get gradient? By the way, I want you to remind us how do we get gradient. How do we get gradient? Yes, Peter. Change in the quantity along y, and in this case, along y we have the voltage, and along x-axis we have the current. Okay, so change in y divided by change in x. So our gradient in this case is going to be change in v over change in r. Now coming back to this relationship, we have said v is equals to r times I. If we divide both sides by I, how is our equation? V over I is equals to what? To I. Is that true? So that is to say, because now we can relate this with our gradient. Yeah? Our gradient is V over I. Our equation here, V over I, is I. So that is to say, the gradient of this graph is going to be our resistance. So when you draw a graph of voltage against current and calculate the gradient, that gradient represents the resistance. Okay? That represents resistance. So I will give you some work that you will do during your own time. You have the results from your group, so during your own free time, I want you to draw a graph using the results from the group. So I would expect each member to draw a graph, but you will use the results from your group. Is that okay? Now, as we come to a conclusion, I want us to look at one example where we apply Ohm's law. Let's look at one example where Ohm's law is applied. Let's look at this question. It says a wire of resistance 20 ohms is connected across a battery. Connected across a battery of 5 volts. And the question is, what is the current flowing in the circuit? What is the current flowing in the circuit? What is the current flowing in the circuit? Are you through copying the question? So maybe before we solve that numerical problem, there is a unit that we are introducing here called the ohm. Ohm is a unit of resistance. We have said when you divide voltage by current, you get what? Resistance. Now from this relationship, we know voltage is given in volts and current is given in amperes. So if we were to derive the unit from the formula, we would say resistance is given in volts per ampere. Okay? So now 1 volt per ampere, 1 volt per ampere is what we call 1 watt, 1 ohm. And the symbol for ohm is that way. So the unit of resistance is called ohm. Ohm. Okay? That's why we are having it here. A 1 resistance 20 ohms is connected across a battery of 5 volts. Then we are asked to calculate the current. So based on that relationship, can one student come forward and work out this problem for us? What is the current? What is the current? One student to work out this. One student to work out this. Nani, I have several hands. You wish to do it for us? Come forward, come forward, come forward. Let us appreciate him for volunteering. We see how he's going to proceed with the working. Maybe you can write at the center so that we can follow the working. He has started, just before you move on, he has started his working from expressing the formula. That is to say, whenever you are working out a numerical problem in physics, you start by the formula. You state the formula. Very good. Move on. So therefore, current is equal to let's follow his working. Let's follow his working. Just move on. Just move on. Just move on. Just move on from the figures that you have. Just move on with the figures that you have. Where they are. You can assume your seat. Don't be a Now, let us look at this working. Any problem with the working? What is the problem with this working? What is the problem with this working? Did he start correctly by writing the correct formula? Yes. The formula is correct. Tick. From there, the procedure which follows is substitution, isn't it? How was the substitution? Is it okay? What is the problem with the substitution? Somebody? I don't want chorus answers, I want individuals. What is wrong with this substitution? Do we agree with that? He has interchanged. In place of the voltage, he has put the resistance. And in place of the resistance, he has put the voltage. So now somebody come and correct that. Somebody come and correct that and give us the correct thing. You can erase that. Now give us the correct thing. How about the answer? Is the answer okay? Yes. The answer is okay. That is very good. Let us appreciate him. Very good. So now that way is correct. It is good that he made that mistake because many of us make the same mistake when we work on our numerical questions, especially at the stage of substitution. So you have to be careful You have to be careful. And one of the things that can assist you is by first writing the values that you are given. Okay? Like now you can write the resistance given is 20 ohms. The voltage given is 5 volts. Okay? Immediately after writing the formula, the next thing, put down the values that you are given. So that when it gets to the stage of substitution, there will be no confusion of which value should be substituted where. So at that point, I want to open the floor for questions. If there is anyone with a question, you can raise your question. If you have any. Before I give you mine, because I'm going to give you a question also. Anyone with a question? Yes, Peter? No, I don't. John? Yes. In graph drawing is asking whether all the points must lie on the line. Maybe before I answer, anyone wants to respond to that question before I give my answer? What do you think? Somebody here is saying that is my conundrum. He's saying yes. Somebody else? What do you think? Let's get more thoughts.
You can find that the points are not lying on the same line, but you can use the line of the best fit.
That is very correct, Makofi kwake. He's saying it is not a must that the points must lie on the what? On the line. But you can draw what we call a line of what? A line of best fit. What is the meaning of a line of best fit? We say a line of best fit, number one, should pass through as many plotted points as possible. And number two, the points which are not on the line should be symmetrically distributed. What do we mean by symmetrically distributed? You can see the way I have put these points here. Like this point is not on the line. This point is also not on the line. But I have put them on the opposite side of the line. So that there is an element of the lines, the points are on the other side and the others on the opposite side. Okay? But we are saying try as much as possible to capture many points as possible. Now that reminds me, ideally this graph is supposed to pass through the origin. Like there's a group, I think it was group 4, their first value was the current 0.00, the voltage 0.0. If they were to draw a graph there as we pass through the others, that is not the case. Okay? So this line, you may find that it is passing not necessarily through the origin, but it is a straight what? Why would we expect that? Okay? We are using what we call in science empirical data. Empirical data is data which is obtained from experiments. Like we have done an experiment, isn't it? And we say experiments are prone to errors. Experiments are likely to be having some errors. We can have an error when you are trying to read, maybe a hazard's error, when you are reading the current, the voltage, and all that. Okay? So it is not likely to be 100% correct. It is likely to have errors here and there. And that is why the graph may not necessarily appear the way it is supposed to be. But the bottom line is that we are saying the graph must be a straight, especially for anomic. If it is an anomic conductor, you will have a different thing altogether, and we shall discuss that when it comes to that time. That was a good question. Any other? So as we wind up our lesson, I will give you an assignment. Assignment number 1 is on drawing the graph. I will explain how you are going to do that. Use the values of the respective groups. Then number 2, I want you to go and research on applications of Ohm's law. Applications of Ohm's law. We have some devices in our daily lives, or that we use in our daily lives, which are designed using the principle of Ohm's law. One, find out, establish whether we have such. And that will come to the end of our lesson. Thank you very much for your participation. You can now dismantle the apparatus. You can dismantle and leave it.